All right, here's a video covering 6.1 in our book, where we try to get a handle on the graph of trig functions. So I'm going to go through this kind of slowly. We'll probably end up doing 2 or 3 videos on this. This first video, the basic idea, what I'd like you to leave this with, is the ability to graph a trig function, kind of like this one that's pictured above here. And in order to be able to do that, we're going to have to think of functions a little bit differently. So I'm going to reference this unit circle. And I also want to teach you these 4 vocabulary words. I think they'll come in handy both in their own right and also in order to create the graphs of these functions. So first off, when we're graphing these functions, this is a little bit problematic. Up to this point in the class, when you've thought about sine of something, you've seen sine of t, right? Sine of t, what that meant up to this point in the class was t was your angle here, and the sine of t referred to the height on the unit circle if we measure an angle of measure t, and like we've been talking about, counterclockwise from the x-axis here. So for example, pictured here in this unit circle, t looks like it's about pi over 3, 60 degrees, aka pi over 3. I don't know if it's exactly that, but that's about what it looks like to me. And that takes us to this point on the unit circle. And at this point on the unit circle, my y value corresponds to the sine of t. So if I'm assuming that t equals pi over 3, then the y value on the unit circle right here, well, we have these memorized off our unit circle. The x coordinate would be 1/2, and the y coordinate would be root 3 over 2. So what that tells me is that the sine of pi over 3 is equal to root 3 over 2. And you're like, yeah, I get it. That's unit circle. We had that memorized in the last section. True, but the letters are going to change. And that can be really problematic because we're going to be thinking about these in terms of graphs. And when we're thinking in terms of graphs, we typically graph up into this point when we're talking about functions, the x-coordinate on this horizontal axis and the y-coordinate on this vertical axis. But now that's a little bit different because when we're thinking about trig functions, the input is the letter t, and the output is either an x or a y, depending on whether we're talking about the cosine function or the sine function. So things are going to get a little bit different. What we're going to do to make this all jive with how we've thought about functions is we're going to let the input to our functions, aka the angle here that we've been talking about, we've used the letter t up to this point in the class. In this section, we're going to use the letter x. And we're going to graph x on the x-axis. So over here, we got the x, and I want you to think that the x is the angle. It's what we used to refer to as this t right here. And then the output for this function will either be the x-coordinate or the y-coordinate on the unit circle. If we're talking about sine, it's the y-coordinate on the unit circle. If we're talking about cosine, it's the x-coordinate on the unit circle. But instead of thinking about it as the x and y-coordinate on the unit circle, because I think that'll be confusing since we're already using x here, think about it as the output to this machine. So the input, we'll first do this one here. If I have y equals sine of x, the input, the x value, is the angle, and the output, the y value, is the height on the unit circle at that angle. So let me try to first graph y equals sine of x. If I'm graphing y equals sine of x, what I want to do is I want to think about, okay, what is the height on this unit circle when x, the input into this function, which we use the letter t to denote in this picture, is 0. Well, if the input into the function, the angle is 0, we're talking about this point right here, and the height right here, because height corresponds with sine, is 0. So when the input is 0, the output should be 0. But if my angle, the input into the function, is pi over 2, I'm talking about this point, and at this point the height is 1. So what that means is the output should be 1 right here. When I graph y equals sine of x, it better go through this point and through this point. And similarly, the height at pi is 0. The height at, because right here, the height is 0. The height at 3 pi over 2 is negative 1. The height at 2 pi, well, that's just getting me back to where it was at 0, right? That's talking about this point. I get here. And I can do that thing for negative angles, negative pi over 2. If I measure pi over 2 in this direction, that gives me a height of negative 1, and negative pi, and negative 3 pi over 2, and negative 2 pi. And so if I could connect these dots intelligently, that would end up giving me the graph of y equals sine of x. Well, it turns out that intelligently kind of looks, well, I don't know how intelligent this is. Kind of makes this nice smooth curve. And I'll do the same thing over on this side as best I can, which is not very good, frankly. But don't worry, I have video backup. So what this is doing, this is just a little thing that I found online, a little animation. It's keeping track of the output for the sine function and then also for the cosine function. So right now we're talking about sine, this red thing, for all these different angles. So when the angle is 0 right here, the height is 0. Talking about that point right there. And then it continues going, right? We're going counterclockwise. So 0, pi over 2, pi, 3 pi over 2, 2 pi. And you can kind of see it trace out those different points, and it has this nice curve. That nice curve is what I was trying to get when I drew it over here. So it would be good for you to know that the starting spot, and wow, this is a horrible picture. I don't know if going over this is going to make it any prettier, but I'm going to try my best. The starting spot, if you want, for y equals sine of x looks something like what I have here in blue. Unfortunately, that's just the tip of the iceberg for this section. We're not just interested in this starting spot. We're interested in transformations of this graph. So function transformations, maybe thinking back to Math 111, there's a lot to it. We got to understand what this 3 here does to this graph, the 2, this pi, this -1. And it turns out that we're going to use these words to describe the effects that those things have on the graph. So that's what I want to get into now. So what I'm going to try to do in red is sketch this graph up here. But before I do, I want to introduce you to some vocabulary words. And in order to give you general definitions for these vocabulary words, instead of always just referring to this example, anytime we talk about trig functions, in this section it'll just be sine and cosine, we're gonna use these letters. I'm gonna say a. I'm not even gonna write trig. I'm gonna write a sine of bx. That's supposed to be a b. Plus c plus d. And some books put a minus c right here, but I think it's more confusing to write it that way. What I want to do is tell you how to define these 4 words, amplitude, midline, period, and phase shift, in terms of a, b, c, and d. So I'll do it with this example where a is equal to 3, b is equal to 2, c is equal to pi, and d is equal to -1. So first, the amplitude. When we're talking about the amplitude of sine or cosine, it turns out, all we're talking about is kind of how tall it is. And when I say how tall, really what I mean is from the middle of this graph to its highest point, right? So from here to here. How high does it get? 1. From 0, it goes up to 1. The amplitude is just kind of the height of this graph. The way you can think about it as a definition is it's 1/2 the max minus the min, the max y value minus the min y value, and that's completely true. The max y value is 1, the minimum is -1, 1 minus -1 is 2, and half of 2 is 1. Okay, I guess, it was easier to just think about it from here to here was 1. And in this case it is, but I think you'll find when you have a whole bunch of transformations, it's nice to be able to fall back on this definition. A very nice thing ends up happening is the only, out of these 4 letters right here, A, B, C, and D, the only thing that affects the amplitude is A here. And if you think back to transformations, A and D are your vertical transformations. This just shifts it up or down. So really it only makes sense that this thing makes it taller or less tall if you want. So the amplitude of F, it's always given by the value of A. But you got to be a little bit careful there. If A is a negative number, we don't want to say it has a negative height. So instead of just defining the amplitude to be A, we're going to define the amplitude to be the absolute value of A. What I'm saying is in this case, where I have 3 sine of 2x plus pi minus 1, if you ask me what's the amplitude of that function, I just said the amplitude is equal to 3. Why 3? Because A equals 3 and the absolute value of 3 is equal to 3. That's the amplitude. 1 down. Midline. Midline of F just describes this middle that I kind of referred to already. Right? The midline of this graph that's pictured here is 0. The average height, if you want, loosely speaking, is 0 here. Okay. How could I define midline in terms of these different letters? Well, it turns out that it's just D. Whatever D is the midline, which sort of makes sense. The midline starts out at 0 if you buy that from this picture. Then the only thing that's going to move this up or down is D. And if it moves up by, 3 units, then the midline would now be at 3. So it's whatever D is equal to. In this case, D is equal to -1. So my midline for the graph that I'm going to draw in red is at -1. And that's supposed to be a D, even though it looks kind of weird. Amplitude and midline are the only 2 things that deal with vertical transformations. Period and phase shift deal with horizontal transformations. So I'm going to talk about those now. The next thing I want to talk about is the period of one of these functions. All the period is, loosely speaking, is how long it takes for this function to repeat itself. So if it starts at 0, it kind of repeats itself when you get at 2 pi. If I started drawing it right here, what I do would look exactly like what I do when I start here. If you have trouble with that, another way you can think about the period is it's the horizontal distance between two consecutive maximums. So from here to here, how far did I travel horizontally? 2 pi, I traveled horizontally. Similarly, it's the horizontal distance between two minimums, if you want to think it that way, or it's just how long it takes to repeat. And the way you can figure out the period is if you first buy that the period in this graph is 2 pi, that my period kind of starts out at 2 pi whenever I'm talking about sine or cosine, then you just have to think about which of these 4 letters are going to affect the period. What affects it horizontally? Well, A and D just affect it vertically. It's only B and C that affect it horizontally. And C just shifts it left and right. It doesn't affect how long it takes to repeat. Like if I move this whole thing left 10 units, the distance between two consecutive maximums isn't going to change at all. C has no effect on the period. Only B has an effect on the period. You might think that you take whatever B is and multiply it by your period. But remember, the horizontal transformations is all the opposite of what you'd think. This 2 right here doesn't mean that I stretch this thing horizontally by a factor of 2. I kind of compress it inward by a factor of 2. So in this case, well, let me do the more general case first. What I'm going to do is I'm going to take my old period of 2 pi and I'm going to divide it by whatever B is. You have to be a little bit careful. That works out perfectly as long as B is a positive number. If B is negative, you're flipping this thing horizontally, which doesn't affect the period at all, but I don't want to tell you that there's a period of negative 3 pi. Like, that doesn't really make sense. Period is a measure that should be positive. So what I'm going to do is I'm going to divide by the absolute value of B. So the period is always, anytime we have a transformation of sine or cosine, 2 pi over the absolute value of B. So in this case, B is equal to 2. The absolute value of 2 is 2. So it's 2 pi over 2, which is just pi. So what that means is when I draw my red graph later on, it's going to repeat every pi, not every 2 pi like I do down here. Finally, the phase shift. You can kind of think about the phase shift as what happened to the starting point. And starting point is a term I probably shouldn't use because these graphs never really start or end. They go forever in both directions. There's arrows at the end of these guys. But if you kind of think about this 0, 0, this origin as being the starting point of my original graph, my graph in blue, what the phase shift does is it tracks where this point goes in the transformed graph. So this 0, 0, where's that point end up when I transform it, when I apply all these different things? Specifically, what is its x coordinate after I apply these 4 transformations? Well, again, A and D only affects it vertically, so I don't have to worry about that. I only have to worry about B and C. And maybe, I don't really expect you to remember this, but when we talked about horizontal transformations, maybe you remember that you applied C first, and then you applied B. So in this case, C is pi. I see that plus pi. That means that this point, I'm going to move it to the left by pi, the opposite of what you'd think. I would move it over here. But then I'm not done because then I have to apply whatever B is, and in this case, B is 2, so that kind of compresses this inward by a factor of 2. It would end up over here at negative pi over 2. If you follow that, great. If you don't worry about it. I'll just give you a formula for it. The phase shift of F is always negative C over B. Negative C because this kind of goes in the opposite direction, and then divided by B because this divides instead of multiplies. So in this case, the phase shift of F would be negative pi over 2. It's worth pointing out that some books don't like this formula having a negative right here. So they write A sine of Bx minus C plus D, and then they can just say the phase shift is C over B. I think that that's really confusing. I think it's easier to define C as whatever's written here, and then remember this is your formula. So always be consistent with these. So the first thing you want to be able to do is answer these 4 questions. And you can memorize the formulas, that's totally fine. I just felt guilty telling you the formulas and not explaining where they came from in terms of transformations. But really what I would like you to be able to do is apply those transformations to come up with this graph. So I think the easiest way to do that is to start with the midline. So my midline should be at negative 1. What I'm going to do, just to keep track of this isn't actually part of my graph, but I'm going to draw this little dotted line right here. So I sort of remember that this should be the middle of my graph. This is my midline. And that's the only thing I'm going to do with midline. So in my head, I'm kind of checking that off, like, yep, counted for that. Now what I'm going to do is I'm going to think about the amplitude. So the amplitude is 3. What that means is this graph, should, at its maximum, be 3 units above its midline. and its minimum be 3 units below this. So really my graph should go, -1's the middle. If I count up by 3, I'm up here to -2. So maybe another dotted line here. Again, this is not part of your graph. These are just guidelines to help you draw things later on. That's the highest this thing should ever get, and the lowest it should ever get is down here at -4. 3 below my midline at -1. So later on when I draw this graph, I'm going to draw something in between these two dotted lines, centered at this dotted line. So where am I going to start it? Well, I have to look at my phase shift to figure out where I'm going to start it. This graph used to start kind of in the middle at 0, 0. My phase shift is -pi/2. So the middle vertically is moved down to -1, but horizontally it has to move over to -pi/2. What I'm saying is this point right here, this big red dot, is kind of where this dot goes when you apply all the transformations. This is going to be my starting spot. So I'm going to draw to the left of this guy and to the right of this guy, and I guess this is the right and this is the left, and kind of think about this point as though it's this point. So this point, which should be on my midline anytime I'm doing the sine graph. And I just figure out how far left and right it is based on my phase shift. And now what I want to do is I want to look at two things. I want to look at its period. That'll tell me how far I have to go for it to repeat. So in this case, the period is pi. So what that means is that by the time I get pi above or below this point horizontally, so pi above it is right here, another pi above it is right here, another pi above it would be out here, pi below it is right here, another pi below it would be out here somewhere. When I get between these dots, I want to do a full revolution in between these dots right here. So remember, a full revolution is going from here up and then back down over to the center. So to get from here to here, I want to go up and then back down and then over to this point in the center. The last thing I want to check is the orientation of this guy. I want to check the sign of A here. In this case, A was a positive number, right? It's the positive number 3. So that means I didn't flip this thing vertically. So when I start out at my starting spot here, I want to go up. Why up? Because at your original starting spot, you start out when you're going to the right by going up. So because I went up here, I want to go up here. If this were a negative number here, then I'd just flip. Instead of starting out by going up, I'd start out by going down. I'd go down this way. But it's not, so I'm not going to. So what I now want to do is kind of connect the dots. I want to go from this dot, or from this dot to this dot to this dot, and then back into what this dot does. And what I want to do is a full revolution of my sine graph in between each of the dots. So not up and back down, but up, down, up. Right? A full revolution, remember, was from here all the way over here. Up, down, up. So if I'm going to go up and then back down and then back up, what I want to do, if I kind of space these out evenly, is end up with a graph that looks something like that. Here is one revolution of my sine graph transformed according to these coefficients here, or to these values here, I guess. You can keep going. There's no reason you shouldn't. What I just redrew is kind of from here to here, but really this thing continues on to the right and it continues on to the left. What I really should do is kind of keep going and get through this point and this point and this point. Try your best to keep the general shape. You're going to want to hit a couple of points. Oh, I did a horrible job of hitting that. That should have gone there, and that should have gone there. And here, I can kind of continue this picture. And maybe you'll excuse the messiness because this is really hard to do on a computer, and just call that good enough. I guess I should go a little bit more to finish up the graph. Whoa, that's bad even for a computer. Get something like that. So again, to recap, you're going to be given a lot of things that look like this. And if I give you this on a test, I'm going to give you this on a test. And what I'm going to ask you exactly is, tell me the amplitude, the midline, the period, and the phase shift. And I'm going to do that because I don't want to just grade your graph, right? This might be a total mess, and then what do I do? Like try to figure out how much you knew? That's going to be really hard to do. So instead what I'm going to do is I'm going to ask you all these questions, because if you properly answer these questions, it tells me kind of what you know about the graph. And then you come up with a graph that looks more or less like this, and you end up getting full credit for the problem. So again, amplitude, it's always the absolute value of A. Midline, it's always whatever D is. The period, it's always 2 pi divided by the absolute value of B. And the phase shift is always -C/B. And those 4 facts are true whether it's sine or cosine, either graph you're dealing with. And you might be like, what about tangent, and secant, and cosecant, and all those other ones? We're going to deal with that in another chapter, so don't worry about that. For now, it's just sine and cosine that I want you to be comfortable with. In order to not make a super long video, I'm going to stop this here. But I have another example. It's almost identical. I'm going to do it below. The only thing that changes is I changed all these different letters, the values in there. And instead of sine, it's cosine. Just want to show you how that looks. So I'll do that example in the next video, and then there'll be a third one where you kind of work backwards. You look at a graph, and you determine those 4 things, and then you tell me what the equation of it is. But those will be different videos, so I'll stop this one here.